Hello, my name is Neil Paulimus, and I'd like to welcome you to the second of our fall series describing various enhancements that have been made to Statgraphics 19. I've decided this fall, rather than doing long webinars once a month, to try to do a webinar approximately every 2 weeks, but to keep them to between a half an hour and 45 minutes. The topic today is enhancements to the design of experiments. And I will remind you again that GoToWebinar offers the ability to submit questions, and I'll try to answer whatever questions are sent to me at the end of my formal presentation. Now, there are two major features that have been added to the Statgraphics 19 Design of Experiments wizard. The first is the construction of what are called alias optimal designs. Alias optimal designs are computer-generated designs, which not only attempt to maximize the efficiency of the design with respect to estimating the statistical model included for that design, but also attempt to minimize aliasing due to terms not in the current model. It's sometimes possible to trade off a little bit of design efficiency in order to reduce quite dramatically the aliasing due to other terms. The second feature we'll be talking about is the augmentation of existing designs. That is, adding additional runs to a design that's already been performed in order to maximize the design efficiency of the final design. Now, I'm going to start this presentation by generating a typical screening design, in this case for 6 factors, and then contrast that later with an alias optimal design. You're looking now at Statgraphics 19. As I said, I'd like to start by creating a fairly typical screening design for 6 factors. To do that, I'll go to the menu to DOE, and then over on the left, select Experimental Design Wizard. Now, the Experimental Design Wizard in version 19 is not much different than what it was in 18. You still have 12 steps you need to go through. First, you start by defining response variables. These are the variables that you want your mathematical models to be able to predict once you've performed the experiment. I'm going to just take the default here where my response is called var_1. That's enough to demonstrate what I want to demonstrate today. The second thing I need to do is define experimental factors. Now, as I said, I'd like to study, in this case, the effect of 6 factors. And we'll just call them factor A through factor F. They'll be continuous factors, meaning that they can take any value over some range. And I'll just take the default range of -1 to +1 for each of the variables. Typically, you'd put in some real values depending upon the variables. But again, to demonstrate what I want to demonstrate, we can just take the default ranges. Okay. Now you can see information start to fill out the Design Wizard window. And as I said, we have 6 factors, all of which are controllable, and we'd like to experiment with them between -1 and +1. Step 3 is where I actually select an experiment to be performed. In this case, I have 6 process factors, and when I push the options button here, you'll see that you have a choice of different types of experiments to perform. We could do a screening experiment, a response surface experiment, a multi-level factorial, an orthogonal array, or a computer-generated design. I'll start with a typical screening experiment. Screening experiments are experiments in which you hope that the important factors will show themselves so that you can study them in more detail later. When you see the selection of designs, you'll see that you could choose a factorial design, a fractional factorial design, a Plackett-Berman design, various choices. For today's illustration, I'm going to pick a Plackett-Berman design. Now, a Plackett-Berman design is a 12-run design for those 6 factors. It's resolution 3, which means it's a main effect only design. We have the ability to estimate the average effect of each of the 6 factors, but typically any interactions between the factors will be confounded with the main effects. In addition, there are 5 degrees of freedom to estimate the experimental error. When I select Plackett-Berman and then press OK, you'll see I have a few other choices. I could add some center points to the design. I could randomize the order of the design. Again, I'll simply take the defaults here, and you'll see that 12 runs have been added to my window. For a Plackett-Berman design, each of the factors, in this case there are 6 factors, is run 6 times at its low level and 6 times at its high level. So let's just take that design, press OK, and you'll see here it's a randomized design in 12 runs with 5 degrees of freedom for the error. Now the next step I intend to perform is step 4. Step 4 is where you specify the model that you wish the experimental design to estimate. It's been set by default to linear because that's typically what's estimated by a Plackett-Berman design. You could ask to estimate 2-factor interactions, but with just 12 runs, we don't have enough runs to estimate all those terms. So we'll just keep it at linear and then move on. Step 5 says select runs. That's only used if you want to run just a subset of the runs. In this case, we're going to run all 12 runs, so we don't need to worry about that. I do, however, want to go to step 6. Step 6 is where you evaluate the design. And there are 3 tables that I want to show you. I want to show you the model coefficients, the alias matrix, and the correlation matrix. Now, the model coefficients gives me information about how well I'll be able to estimate the coefficients in the model. In this model, there are 7 coefficients, a constant term, and main effects for each of the 6 factors. You'll notice that the standard error of each one of those coefficients is 0.288675, which is as small as it could be, incidentally, for a 12-run design. You notice over here the column labeled VIF, that's variance inflation factor. Because they're all 1.0, it means that the standard deviations, the standard errors, are not inflated. They're as small as they can be. Part of the reason they are, you can see if you go down here to the correlation matrix. The correlation matrix shows how correlated the different coefficients in the model are with each other, the estimates of those coefficients. You'll notice that it's a diagonal matrix here with 1s on the diagonal and 0s off the diagonal. That's indicative of an orthogonal design, where each of the effects has no influence on the estimates of the other effects. That's why you're getting, in this case, actually a D-optimal design. So with respect to the coefficients in the model, they're all clear of each other. The other thing I want to look at, though, is this thing called the alias matrix. The alias matrix shows the confounding of effects not in the model with effects in the model. You'll see on the left-hand side the constant and the 6 main effects. Across the top, you'll see terms like AA, AB, AC. AA is a quadratic term. That's like an x squared. AB is an interaction between factors A and B. That's like x1 times x2. Now, in this case, I'd like to push the right mouse button and go to Pane Options and not include the curvature terms. For this illustration, I just want to worry about the two-factor interactions. Well, what you can see if you look at this table closely, and it goes over a little to the right, is that each of the main effects is disturbed by interactions not involving itself, right? You'll see a term here like minus 0.3333 under BC. That means that when you're estimating the main effect of A, you're not really estimating just the main effect of A. You're estimating the main effect of A minus 0.3333 times the BC interaction plus 0.3333 times the BD interaction, and so forth. Now, if you assume there are no interactions, or if you assume that the interactions are relatively small with respect to the main effects, that's not a problem. But that may or may not be the case. What we're going to do next is actually generate something called an alias optimal design. What that is going to do is allow us to basically reduce the impact of these terms that are not in the model by backing off a little bit on the D-efficiency of the design. We'll let the standard error of the terms that are in the model be a little larger in order to reduce the effect of terms not in the model. Now, one other term I want you to see down here, it's a line called trace A prime A. It's equal in this case to 6.6667. This alias matrix is A, and if you take A prime A and take the trace of it, you get a measure of just how much confounding there is in this particular design. Remember that number, 6.66667, because we're going to compare it in just a moment to an alias optimal design. I've now cleared the Statfolio, and this time I'm going to create for you an alias optimal design. We start the same way we did before. We'll go to DOE, Experimental Design Wizard. Step 1 sets the response. Step 2 specifies 6 continuous factors. Step 3, where it asks me to select the design, is where the first difference is. When I press Options, rather than asking for a screening design, I'm going to ask for a computer-generated design. When I press OK, the only thing you'll see is that it knows it's going to do a computer-generated design. And when I press OK and look at the design summary, you'll see in step 3, we haven't actually defined the runs yet. Okay. Now, step 4 is where we specify the model. I want to keep this similar to the Plackett-Berman design, so I'm going to choose the linear model with the 6 main effects. I'm then going to go to step 5, select runs. This is the step we skipped with the Plackett-Berman design because we already had the runs. For an alias optimal design, though, you need to go here. Now, in general, when you do a computer-generated design, you tell it what type of efficiency you want to optimize. Do you want an I-optimal design, a D-optimal design, an A-optimal design, a G-optimal design? They were all available choices in version 18. The new choice in version 19 is to ask for an alias optimal design. Now over here where it says number of base runs, I'm going to type 12 to make it similar to the Plackett and Berman design. And before I push the create button, I'm also going to go over here to where it says alias options. On this dialog box, you tell it what terms not in the current model are you concerned about. Do you want to reduce the aliasing of? And to make it similar to what I did a few moments ago, I'm going to tell it I'm worried about two-factor interactions potentially disturbing the effect of the main effects, my estimates of the main effects. I also need to go down to where it says minimum relative D efficiency. This is where I tell it how much I'm willing to give up with respect to the D efficiency, the estimation of terms in the model, in order to reduce aliasing due to terms not in the model. Now, it turns out in this particular example, it works nicely if you tell it to give you at least 90% D efficiency. You may need to play around with that to get a good model. In this case, 90% works pretty well. I also will tell it how many alias reduction attempts to make. Now, in order to get an alias optimal design, it has to implement some sort of a search algorithm. And depending upon the starting conditions, one attempt may get a better model than another. The goal, though, basically is to minimize the trace of A transpose A, that measure we saw a few moments ago, while having at least, in this case, 90% D efficiency. All right. Now I'm set, so I'll go down here and push the create button. And what it's going to do is it'll begin searching for that alias optimal design. And you can watch it go through its 25 attempts. There, it's done. And it's come up with 12 runs for factors A and A through F. Now you'll notice in most cases, the factors are run at their high and low levels, except it's picked one factor, in this case factor D, where it's run once at minus 0.5 and once at plus 0.5. That's pretty interesting. You'll see that in just a second. The D efficiency of the design was 90.45. The trace of A transpose A dropped all the way from 6.66 to 0.59. Quite a reduction in the alias efficiency. So let's press OK, which will select that design, and then go back to step 6 and do an evaluation. Remember, last time I looked at the model coefficients, the alias matrix, and the correlation matrix. If you look at the model coefficients, you'll notice that the standard errors are a little bit larger than they were before. The first time around, all the standard errors were 0.288675. Now the standard errors on the main effects have increased a little bit. And you can see the variance inflation factors, which measure how much that standard error has gone up, are around 1.2. Now that's actually pretty small. That's a fairly small change in the standard error. And look now what it's done with respect to the alias matrix. Again, I'll get rid of the curvature terms. And you can see the alias thing has basically disappeared. There is some aliasing with the constant term. That's typically not a big deal, since the constant is the estimate of the response in the center of the experimental region. But it has gotten rid of all the aliasing with respect to the main effects. And as we mentioned, the trace of A transpose A has gone down quite dramatically. The second major enhancement to the DOE wizard in version 19 has to do with augmentation of designs that have already been performed. And as an example, I'm going to go ahead and load up a data file called chemical reaction 2, which is an experimental file that we ship with the program. This is a design that's already been performed. If I go over to the data sheet, you'll see that there are 5 factors: feed rate, catalyst, agitation, temperature, and concentration, and a single response variable reacted. What the experimenters wanted to do is find a combination of these 5 experimental factors, which would give them a large value for percent reacted. Okay. Well, let's go back here and analyze that first design. I'm going to press step 8, ask it to analyze the experiment, and you'll see that it's estimated main effects and 2-factor interactions. In fact, if I call up the standardized Pareto chart, you'll see estimates for A, B, C, D, and E, and various combinations. Those are the 2-factor interactions. Now, on a standardized Pareto chart, anything to the right-hand side of the line is statistically significant at the 5% level. Anything to the left-hand side is not. Well, this experiment worked out pretty nicely, I think you'll see. There are 3 factors that seem to be important: catalyst, temperature, and concentration. There are also a couple interactions between those factors. There's the BD interaction and the DE interaction. Okay. Now, at this point, what the experimenters decided to do was to add some additional runs to this experiment. This was actually a set of 19 runs that was being used for screening. They decided that they'd like to add some additional runs in order to estimate quadratic effects. Things like catalyst squared, temperature squared, concentration squared. To do that, to augment the current design, I can go to the experimental design wizard, back to the wizard window, and go to step 11, which is augment design. It's telling me that the experiment will be changed, so I could save it if I wanted to. I'm not going to do that. I'm just going to go to the augment design dialog box. Now, this is fairly similar to what you would have seen in version 18. You can add replicates, you can add a fraction, you can add star points. What's new in version 19 is this optimize button. The optimize button lets you tell it that you'd like to add, for example, 6 runs to the current experiment. 6 runs in order to estimate, and here I'll push new model, in this case, a quadratic model. Now, I'm not going to estimate the full quadratic. There were 2 factors that didn't seem to be significant. That was factor A and factor C. I'm going to take out, by double-clicking on any interaction or quadratic term involving A or C. Okay, that should get me down to a model with 5 main effects, 3 quadratics, BB, DD, EE, and 3 2-factor interactions. All right, that's the model that I want to estimate once I've done the additional runs. The other thing I want you to see is what happens if you push search options. Search options lets you specify the criteria for optimizing the design. Is it I efficiency, D efficiency, A efficiency, or G efficiency? I'm going to leave it as D efficiency, which has to do with the ability to estimate the coefficients in the model. You can also tell it over here how many continuous factor levels to consider. Again, it's going to be doing a search, and if you tell it consider 5 factor levels, it'll try 5 levels between the lowest and the highest value that you earlier had specified. All right, so we'll just push cancel to take the defaults and then push optimize. And what you can see is it went through a search procedure, but now added 16 runs to the original 19. Those factors where I wanted only the main effects are run, you can see, at their high and their low level. That's A and C. Factors B, D, and E have several runs halfway between the high and the low. Final D efficiency of the overall design with respect to that new model turned out to be 49.6%. I hope you'll try out those 2 new features of version 19. I think you'll find that there are times when they are really advantageous in setting up an experiment. There are additional videos you can look at www.statgraphics.com/instructional_videos. You can also check our website for upcoming webinars. I believe we have a webinar upcoming in about 2 weeks on fitting mixtures of Gaussian distributions. That's also a very interesting topic.